Which came first, the internet or the World Wide Web? Who thinks the internet? Who thinks the World Wide Web? A lot of people not thinking again, okay? Actually, it's the internet. The internet came first, and the web computer application was put on top of the internet. So the internet had to exist before the web. But CERN developed the web in 1989, it's 30 years old, and gave it to the world for how much? How much did CERN charge the world for the World Wide Web? Somebody must know this. No? Do you know? You don't know. Ah, you're saying zero. Zero? CERN gave the World Wide Web to the world for absolutely nothing. Yes, it did. CERN gave the World Wide Web to the world for nothing at all. Okay, so those are two strategic missions. Do the research and develop the technology to do the research, and the technology becomes immediately available to the rest of the world to do other things. Now, another thing that we do is to train the scientists and engineers of tomorrow. That's one of our mission statements. That's why I am here. Because what are we doing today? I'm trying to inspire and encourage you guys to understand a little bit more about science, and hopefully some of you will become scientists, engineers, technical people, computer scientists, that sort of person. Who thinks they might want to be a scientist, engineer, computer scientist? Ah, well done. We've got a lot more hands in the air this time. Well done. That's really good to see. But it's also about understanding science as well. Okay? How do we do it? We invite people to come to CERN, to visit CERN. People from India have visited CERN. I've seen Indian students at CERN. And we have more than 150,000 visitors every year. Half of them are educational groups, schools or universities. And we have programs for teachers. And we invite teachers to come to CERN. More than 1,000 every year. Again, I'm aware that the numbers that I talk about in India are maybe not so big, but 1,000 teachers from 20 different nations, and we can talk to them in more than 20 different languages. How can we do that? How can we talk to people in more than 20 different languages? Remember, we have people working at CERN from more than 100 nations. So it's easy for us. We can give programs in Chinese, in Korean. We could give programs in Hindi, actually. We haven't. We can give them in many different languages. Now, who thinks that they might want to be a teacher? Okay, congratulations to the half a dozen people who've put their hands in the air. Let's give them a big round of applause. Well done. Why do we give them a big round of applause? Because teachers are really, really, really important people. Why? Because they hold the future in their hands, teachers. Okay? Without teachers, there's not going to be a future, at least not one that we might want. Okay? So teachers are really important people. So when they come to CERN, what do we say to them? Thank you. Well done. So we say, right now, with a big round of applause, a big thank you to all the teachers who brought you here today. Okay, thank you very much. So, we try to train the scientists and engineers of tomorrow, and we try to unite people from different countries and cultures, because there are 100 nations represented at CERN, and we all work together peacefully. We don't fight. Some of these people come from be fighting, but they don't fight at CERN. Okay, we work together, collaboratively. Okay? So let's get now a little bit closer to the science. That's the geography, the politics, the sociology. But remember those things, because they're extremely important. Okay? So, here's a picture of our universe, the evolution of our universe. The whole universe was in a hot, dense state, and nearly 14 billion years ago, expansion started. What? Wait. Now, this young lady has been watching the Big Bang Theory on television, and she knows that Sheldon knows about this. I am not surprised that some of you other guys don't watch this, but our model for which we have evidence for the evolution of the universe is that it started with a Big Bang, rapid expansion, and then it's growing still. Is it going to continue growing? Is it going to reach a steady state? Is it going to collapse? Are we going to have a big crunch? Well, these are some of the questions we're trying to answer, okay? But the point here is, we think the universe is 13.82 billion years old, but not only do we think, but we have evidence for it, okay? We have evidence for this, because another big message for you is that scientists work on evidence. So, you might know that there are sort of two major categories of scientists. There are guys who are called theoreticians. And what do theoreticians do when they come into work in the morning? They think. And they write down theories. And they make proposals. But there's another bunch of people, like Ashana, who come in and they actually do something. Not just think. They think as well. What do they do? Well, they think of experiments to do which will verify or falsify the theories. Sometimes the experimentalists find things that theoreticians haven't thought about. And then the theoreticians have to start thinking to explain this, okay? But often there are many theories, but the theories are only theories until they are verified by experimental evidence. And that's how science works. We don't believe this by saying, oh, I believe the universe is 5 billion years old, or I believe the universe is 20 billion years old. We have evidence for this, okay? So, here's a ruler. Here's a ruler. 10 to the minus 32 centimeters. I don't know whether you understand this notation or not, but your teachers will talk about it with you. To 10 to the 28 centimeters, okay? Now, the scale that we move around in is actually somewhere around the scale of a meter, 10 meters, 100 meters, okay? We're all about 2 meters tall, some of you. I'm not 2 meters tall, but I'm not far from 2 meters. So we live at this scale. Who is that? Albert Einstein. Albert Einstein, okay? If you want to look at the very big or the very far away, what do you use? Lots of guys shouting from over here. I want guys shouting from over there as well. Telescope, don't be frightened. We have the left-hand team, the right-hand team. I'm going to split you into two teams now, left-hand and right-hand. So it's a competition now. When I ask you something, you have to shout out, and we'll see who wins, whether it's the left-hand guys or the right-hand guys, okay? So, what do we use if we want to look to the very far away or the very big? Pretty good, it was equal. Okay, telescopes. So we use telescopes, and the telescopes that we have, well, we have many, but the ones which are notable are in the Atacama Desert in Chile. The ALMA telescope and the very large telescope, the VLT. I've been there in Chile, Atacama Desert. It's completely dry. Drier than where we are here. Okay, drier than Bangalore. It's really dry, which means there are no clouds in the sky, which is really good if you want to investigate, if you want to look at the stars, look at the galaxies. In fact, the people who work at this place, much smaller than this school, by the way, the people who work at this place, but very large telescopes, they live underground. They work underground. Why? Anybody know? Left-hand team, do you know why they work underground? There's a guy putting his hand up at the back. Yeah? Do you know? Where's the microphone? You have to keep standing up. He's right at the back. Go and give him the microphone. Run, run, run. Why do they work underground?
To create vacuum.
To what?
To create vacuum.
To create a vacuum? No. Guy at the front. Just shout. What? It's too hot outside. It is quite hot. But no. Yeah, you were here yesterday. No, you weren't here yesterday. So he says to prevent light pollution. That's exactly right. If you want to look at the stars, well done. If you want to look at the stars and the galaxies, you don't want light pollution. So they actually live underground. Okay? They also have this remarkable device which is called the Hubble telescope. Okay? Hubble telescope. Where's the Hubble telescope? In space. It's in space. When they first put it up, it didn't work. The optics didn't work. What did they do? I know that India has a very important space program, and you can send devices into orbit around the Earth, satellites, things like that. I know, so you should know. What did they do? Some of you guys are going to work in that industry, I'm pretty sure. Okay? What did they do? Well, they sent astronauts up in a shuttle to fix it. These astronauts got out of the shuttle, they did a spacewalk, and in their big space suits where they can hardly move their hands, they fixed it. Okay? Remarkable. And then we have something called the International Space Station, flying about 400 kilometers above our heads, flies around the Earth every 92 minutes. Every 92 minutes, it has a particle detector, a camera on it, looking at particles that are coming at us from outer space. Okay? So we have that instrument. And that instrument is actually controlled from CERN. If we want to look at the really, 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 really tiny, the really, really small, what do we use? Everybody knows that we would use a microscope. Very good. What's the best microscope? You all think it's an electron microscope. Actually, it's the LHC. The LHC can probe down to distances of 10 to the minus 16 centimeters. Okay? What we know about what we're made of, what things are made of, using our microscope and microscopes, the other microscopes, matter's made of molecules, atoms, nuclei, which are made of protons and neutrons, which themselves are made of other particles, quarks and gluons, which themselves may be made of something else. Okay? So that's the picture we have of matter. And these two ends of the ruler used to be separated, for example, when I started working in this field, but today they actually come together. So looking at the very big, the very far away, looking at the very tiny, the physics, the science is actually associated. Okay, who painted that? Don't expect you to know, but does anybody know who painted that? Well, there's a guy called Gauguin. He was a French painter, lived at the beginning of the last century, or died at the beginning of the last century. He painted that just after his favourite daughter died, so he was quite sad. But nevertheless, here, in French, and very tiny, so you can't read it, he told us the 3 questions that humankind has been asking for thousands and thousands and thousands of years. Anybody know what the 3 questions might be? And these are the 3 questions that, in general, we try to ask and try to answer at CERN. Anybody know what the questions might be?
Where do we come from? Where do we go after our life?
Nice.
Okay, well, not so much about us, but your answer is a really good one. How did the universe begin, and how is it what's going to happen in the future to our universe? Okay? Where do we come from? Where are we going? And the one in the middle, anybody know the one in the middle? Can you guess? What are we made of? Okay, so it's where do we come from? What are we made of? And where are we going? So in general terms, that's what CERN tries to do, is try to answer those 3 questions. Now there's another really important question that humankind has been asking for thousands of years. The 4th question, do you know what that is? Well, I'm looking forward to getting the answer, because the 4th question is, what are we having for lunch today? Now this is a very, very important question that humankind has been asking every single day for tens of thousands of years, okay? So that's important. We facilitate the answering of that question at CERN because we have 3 restaurants on our site, but what we're really trying to do is to answer the questions, where do we come from, what are we made of, and where are we going? And to do that, we built the LHC. So where do we come from, what are we, where are we going? And the aim of particle physics CERN and LHC is to answer those questions. How do we do it? Well, we've talked about it a little bit. We build a particle accelerator called the LHC. Here it is, living in its tunnel. The tunnel is 100 meters below ground. You can go down there, not today, when it's not operational, and it's not filled with, it's not powered, and there's not gas and things like that in it, which is very important. You can walk along here, you can breathe, the temperature is 20 degrees centigrade, there's 18% plus oxygen in the atmosphere, and we know that because we measure it. So you can go and work in the tunnel. You can even go to work on a bike, because there are only 8 access shafts in 27 kilometers. So you have to choose, if you work there, which shaft you go down. And then you get on a little bike, okay? We collide protons. Now, this is interesting. The energy, we measure energy in electron volts. What's an electron volt? Does anybody know? Can anybody define an electron volt for me? No? Never heard of it? Well, it's the energy that an electron gets if it falls through a potential difference of 1 volt. Okay? So that's how we measure energy. It's a strange way, but it's the way we do. Okay? And we have 1 billion collisions per second where the particles collide in the 4 experiments. What are we trying to understand? Apart from the answer to the 3 questions, these translate in a more scientific way into saying, each particle, like a proton, electron, has a mass. Where does it get that mass from? Now, this is related to a big discovery that we made at CERN in 2012. Does anybody know? What?
Yes.
Say it again.
Yes, it's correct. Say.
Higgs boson.
Wow, congratulations. Well done, young man. It's related to the Higgs boson. We'll talk about that in a while. Why is it called the Higgs boson, etc.? So that's one of the things. Another is, what's dark matter? Does anybody know what dark matter is? I'm not surprised, because if you did, you'd have a Nobel Prize. Okay? But does anybody know what we mean when we talk about dark matter? Oh, the young man knows as well, again. Wow.
It's the extra mass which galaxy needs
We don't know
to
what it is.
get its
That's why it's
gravity.
called
Like the mass.
वो तो उसको सारे answer
It's
मालूम
the
Wow.
invisible matter.
है. He should go there.
Wow. Incredible. Well done. Okay? So, the galaxies, we have evidence that there is dark matter. We don't see it, so we're very imaginative. We call it dark matter because we don't see it. But we have evidence for it because we see that the galaxies are rotating too fast to be held together by Mr. Newton with what we see. So there must be more stuff there. But we don't understand yet what it is. And what did the universe look like right at the beginning? After the Big Bang? Well, maybe the quarks and gluons that are confined in protons were free at that time. And we tried to investigate that possibility by colliding not protons, but nuclei of lead. That means lead with 82 electrons taken away. Big, heavy, massive things, and we smash those together. Okay? And then finally, interesting question, what's happened to all the antimatter? Because Big Bang Theory, the theory says that there's equal amounts of matter and antimatter created at the beginning of the universe. But wherever we look, we don't see any antimatter. By the way, what's the difference between a proton and an antiproton? An antiproton is antimatter and a proton is matter. What's the difference? Anybody know? Don't really expect you to know this, but sometimes people do. It's the charge. An antiproton is negatively charged and a proton is positively charged. An anti-electron is negative, an electron is negatively charged, an antiproton is positively charged, okay? But we don't see any neutral antimatter in the universe at all. Where's it all gone? No idea. Maybe you can find out. Okay, we say that the LHC is the emptiest space in the solar system because in the tubes which the protons travel in, the pressure is 10 times lower than on the moon. So we have to have very effective and efficient vacuum pumps, okay? Why? Because if there was air in the tubes, the protons would collide with the air and they would never meet. And we want them to meet and collide, okay? We say the LHC is colder than outer space. What does that mean? And why? The LHC is maintained at a temperature of 1.9 degrees Kelvin, minus 271.1 degrees centigrade. Wow, that's pretty cold. Okay, that's really cold. Interesting question is why? Well, what's the temperature of the universe? Well, as measured by the cosmic microwave background radiation, some radiation that we can detect that's coming at us since 300,000 years after the Big Bang, that we measure the temperature of that as being 2.7 degrees above absolute zero. But the variations in the temperature, this is the variations, color-coded variations, that diagram, that picture, is how we understand how old the universe is. Pretty tricky, but that's where it comes from. Okay? So where are the experiments? We have 4 big experiments. Well, they have to be underground. Atlas, Alice, CMS, and LHCb. I'm wearing a CMS t-shirt today, okay? And Ashana works for the CMS experiment, and actually, officially, although I work mostly with CMS, I am attached to the Atlas experiment. So I should really be wearing an Atlas t-shirt, but because we're talking a lot about CMS today, I'm wearing a CMS t-shirt. Okay, they live underground. What do they look like? Well, this is what they looked like when they were being built. Doesn't give you an idea of how big they are, although there is a guy there, okay? How big is Atlas? Where is that? That's in Germany, the Brandenburg Gate in Berlin. And that's the size of Atlas. Atlas lives in a huge cavern underground, okay? That's the size of Atlas. CMS is smaller, a little bit smaller, 21 meters in length, 15 meters in diameter, a cylinder, but it's twice as heavy as Atlas, in fact. We say it's the hottest place in the galaxy because where the particles collide, the temperature, equivalent temperature, is 1 billion times higher than in the heart of the sun. Nothing gets hot. We don't call the fire brigade. Nothing burns. It's just an equivalent temperature. Okay? Now, you all think we've got an accelerator at CERN. Yeah, we do. But we have more than one. And these are the accelerators at CERN. And this is why you have this here. This is this picture. Why do we have more than one accelerator at CERN? Well, we're more than 60 years old. So we've been building accelerators since 1954. And the first one became operational in 1957. And this guy became operational in 1959. And guess what? It's still working today. It wasn't designed to last this long, but they built it so well that it's still running. So it's a fantastic tribute to the guys who built it. Now, why do we have more than one accelerator? Because you can't take a proton from 0 to very high energy in a single machine. It's like a car. You have to go through the gears, different speeds. So we have them because we're quite old. So, would you like me to start the CERN accelerator complex and take a proton from a bottle of hydrogen and accelerate it to 6.5 TeV? Would you like me to do that?
Yes.
Who thinks no? Who thinks yes? Some people don't care. Okay, but I'm going to do it anyway. All right, so I'm going to take only one particle and send it in the clockwise direction, and I'm going to take another particle and send it in the anti-clockwise direction in the LHC. And they're going to be the blue and the red particle. In reality, there are many, many more particles, but this just shows you what happens, okay? Let's start the beam. Bottle of hydrogen into the proton synchrotron, under the road, now they're underground, into the SPS, into the LHC, and bang! Or no bang? That is the question. Okay, shall we do it again? It's fun, huh? It's fun, look. Now remember, what we got here is a linear accelerator, 30 meters long, accelerates to 50 million electron volts, into this guy built in 1972, into this guy built in 1959, under the road, which I travel on every day, into the fields behind the opposite side of CERN, to a particle accelerator built in 1976, 450 GeV finally into the LHC. Let's do it. Ready? Go! Red beam, blue beam, into the proton synchrotron, into the superproton synchrotron, into the LHC, and bang! or no bang? That is the question. Who thinks bang? Who thinks bang? Who thinks no bang? I got far too many people not thinking here today. This is not good. Are you not used to being asked questions like this, okay? It's very important, is this. Again, who thinks bang? Thank you. Who thinks no bang? Actually, remember, the particles are moving in a vacuum. So there is no bang. Sound doesn't propagate in a vacuum, but there wouldn't be a bang anyway, okay? But it's an interesting question and we can have fun with it. So, no bang for two reasons. There isn't a bang and they're in a vacuum, okay? What happens when they smash together in the camera? They produce all this stuff that didn't exist before. They transform energy into matter, into mass. And all of these particles know a very, very, very famous equation. And they use that equation to do this. What is the equation? E equals mc squared. Who gave us that equation? Einstein, yeah. So we transform the energy of the protons into matter that did not exist. And we try to understand the properties of and identify each of the particles that are produced in this collision. And we do it many times. In Ashana's experiment, they get 40 million collisions per second. That's 40 million photographs. And guess what? Most of them are not interesting. So the first thing they do is they throw away the data from most of them, and they only keep the data from, let's say, 400. And they store that and they analyze it, okay? So 40 million per second become 400 per second. Here you can see that, you'll learn this from Ashana, this is not just one camera, it has different layers of camera which are doing different jobs. They recognize, identify and measure the properties of different particles. What does it look like when you reconstruct it with a computer? It looks like this mess here. And what you have to find is something like that, which might be a Higgs boson decaying into 4 heavy electrons, 4 muons, okay? We produce a lot of data. Who's a computer geek freak? Your teachers must know, are you a computer geek freak? Are you interested in computing? Who's interested in computing? A lot of you, okay. Well, there's a lot of computing you have to do at CERN because we produce 25 petabytes of data every year, and that data has to be analyzed on 1 million IBM PC architecture computers which are distributed around the world, connected by high-speed networks. So first of all, you have to select the interesting events with software and electronics and computers, and then you have to analyze them with computers which are spread all over the world. What operating system do you think those computers are using? The computer geek freaks, the people who are interested in computing. What operating system do you think they use? Linux. Who said Linux? Somebody say Linux? No, nobody said Linux. But if you'd have said Linux, you'd have been right, okay? Linux. So that's the network of computers. There's computers in India that do this job. Okay, that's all the countries. I'm not going to talk too much about that. I talked about education activities. I talked about the teacher schools. I'll talk about summer students in a minute. The teachers, by the way, come from all over the world, and this is the number of teachers that we've met since 1998 when we started the program. We never dreamed in 1998 that there would be this number of teachers that come to CERN. Okay? It's a dream come true. Who works at CERN? Well, you'd probably say there are physicists, experimental and theoretical physicists, but not so many of those doing particle physics, many more doing applied physics and engineering, because we have to build the accelerators, we have to build the detectors, we have to operate them, we have to operate the computing networks, etc. These are the guys, the 13,000 who come from all over the world, who do the physics. And this is what you can be in the next 10 years. Okay? You could be one of these people that come to CERN to work temporarily. Okay? You can also be one of these people who come and work at CERN representing an Indian scientific organization or university who collaborates with CERN. And Ashana can tell you a lot more about that. Okay? What happened? Well, in 2009, the LHC switched on. What happened when we switched it on? Actually, it switched on in 2008 and immediately switched itself off again because it broke. Okay? But it was fixed within a year and it's been okay ever since. So everybody got excited, but the energy was not the energy of today, it was a little bit smaller. And in 2011, the two experiments, the big discovery experiments, Atlas and CMS, started to say, maybe we're seeing something interesting, but they were very conservative. What they were seeing were reconstructions of particle interactions like this, which is an interaction which gives two photons, okay? Or maybe something like this, which gives 4 muons. And then, on the 4th of July, they were brave enough to say, actually, we are sure we've seen something. And the experiment spokesperson for the two experiments, one for Atlas, Fabiola Gianotti, who today is the Director General of CERN. So the Director General of CERN today is a lady. Would you have guessed that? The ladies wouldn't have guessed that, okay? Maybe the guys might have guessed it. But it's absolutely true, and she's just been appointed for a second period of being Director General. The guy who made was a spokesperson for CMS, Joey Candela from the United States. Fabiola is from Italy, by the way. He's back in the United States now at his university, and we have another spokesperson for CMS. They said, we are pretty sure we have a signal which is statistically significant, and we both see this particle at the same mass. So what does that mean? Well, they looked, let's take the 2-photon channel, the Higgs boson decaying into 2 photons. What you do, you take all the events which have 2 photons. You assume that the 2 photons came from the same parent. You calculate the mass of the parent and you plot it. If there was no parent, this would be completely flat. If there was a parent, there will be a bump. And guess what? There's a statistically significant bump in both of those plots. So they said, yeah! And they woke a lot of people up in the audience. Wow, that was a good thing to do. And these are 5 Directors General of CERN. Chris Llewellyn-Smith from the UK, the then Director General Rolf Dieter Heu from Germany, an ex-Director General Herbig Schopper from Germany, Luciano Maiani from Italy, and Robert Aymar from France. and lots of people in the auditorium, and many, many more people on the internet watching. They all celebrated the discovery of the Higgs boson that we talked about earlier. Okay? And the newspapers of the world got excited, and the Nobel Prize Committee in 2013 gave the Nobel Prize to two guys. Peter Higgs from the UK. Okay, many people think he was born in Scotland. He wasn't. He was born in the UK, in England. Well, UK, Scotland as well, sorry. In England. He wrote a paper in 1964 predicting the existence of this particle. 1964. And it was found in 2012. When he wrote his paper, nearly everybody ignored it, okay? And they didn't really start thinking about it seriously until 15 years later. And then they started thinking, maybe we've got to find this because it's sort of a key thing, okay? And they found it in 2012. And this guy's a Belgian guy, François Anglaire, and he wrote a paper within a few weeks of Peter Higgs in 1964 saying the same thing, okay? And he did it with a friend of his called Robert Brout from Belgium. So they wrote a paper together. He wrote a paper by himself saying the same thing, basically. Except he said that with this field that generates the mass, there must be associated a particle. And that's why the particle is known as the Higgs particle and not the Anglaire particle. But why is Mr. Robert Brout not there? How many people can you give a Nobel Prize in Physics to each year? How many? 3. 2. Where is he? Well, unfortunately, Robert Brout died in 2011. And you can't give a Nobel Prize posthumously. Okay? So what the Nobel Prize Committee did is, rather than find somebody else to give it to, there were theoretical physicists who were working in the same field. There were thousands of people who worked on CMS, thousands of people who worked on Atlas, thousands of people who built the LHC. They gave the Nobel Prize to Peter Higgs.